Guys, welcome back to Code.com. Today we are solving the problem which was asked in the coding interview of SAP Labs, Accenture and Accelya. So the title says determine whether two nodes lie on the same path in a binary tree. And the description is given as given a binary tree and two tree pointers, namely x and y, write an efficient algorithm to check if they lie on the same path from root to leaf in a binary tree. In simpler words, we have to check whether x is an ancestor of y or y is an ancestor of x in any way. Okay, and we have to find the efficient algorithm. Okay, so what they mean is, like, let's take an example over here, node 2 and node 4. So node 2 is an ancestor of node 4. So if I am traveling from 1 to 8, then they both lie on the same path. Okay, so I can consider that they both lie in the same path. But if I take the condition of node 4 and node 5, they both don't lie in the same path, like they said, from root to leaf. Okay, so if I am traveling to 8, okay, I encountered 4, but I don't encounter 5 when I am traveling here. And if I am encountering 5, I need to go to 10, but in that case I don't encounter 4. In this case, neither of them are ancestors of each other. Okay, so we have to do this in minimal time. So the naive approach would be that we would first find the path for 4, then for 5, and then we will check if they both are having the same path or not. Okay, but an efficient algorithm, we are going to do an pre-order traversal. What is pre-order? First we will go to root, then to the left, and then to the right. Okay, if you guys don't know this, or if you guys might have got confused, just keep this in mind. We are going to do a pre-order traversal. Okay, and while doing pre-order traversal, what we are going to do is we are going to maintain an hash map. Okay, what does hash map stores? It will store the arrival time and the departure time of that particular node. Now what does that mean? Okay, what does arrival time mean? Arrival time means that at what time, see, like we are starting from a root. Okay, if I am starting from a root, then at what time I encountered this node 2, this node 4, or this node 5, or this node 10. Okay, at what time did I encounter these nodes? So I encountered the root at time 1, and let's say after that I moved here. Then I encountered 2 at time 2, node 4 at time 3. Now you guys might say that if this at this time 4, then I moved over here, and then 5, 6, like that. Okay, this is just an example. Okay, so in this way I have encountered these nodes, and this is the arrival time. And what does departure time means? Now departure time means that suppose this node, okay, I encountered this node, but at what time I traversed all its childrens. That is my departure time. After traversing all the children, I will be visiting this node back. So while going upwards again. So at what time does that happen? That is our departure time. Okay, and our arrival time is at when we discovered that node. That is our arrival time. So you guys might be thinking that, okay, we got that concept, but how is that helpful for us? Okay, how is that helpful for us? So let's take the simple example of 2 and 9. Okay, 2 and 9. So which I will write here arrival and departure. Okay, so which node would be discovered first? Okay, we will discover 2 first. Okay, arrival of 2 first, and after that which node we will discover? 9, because we are traversing like this, right? So obviously 2 will be discovered first, then 9. So this takes place. Oh, sorry. Arrival time of 2 is less than the arrival time of 9. That's for sure, because we are discussing this first. Now, what will be a departure time? Which node will traverse all its students first? Obviously the 9. Because if you have to traverse all the children of 2, you have to go to this subtree, then this, and then this. But 9 will do it quick. So departure time of 9 is less than the departure time of 2. Okay, you got the concept that how this is taking place. Okay. Now when this condition arises, that the arrival time of a node is less than the arrival time of second node. Let's take node A and node B. Okay, I will write here node A and node B. Arrival time of node A is less than arrival time of node B, but the departure time of node B is less than the departure time of node A. In that case, A is the parent. See, as you can see, A is the parent and B is its children. Okay, it means A is an ancestor of B. And if it is the vice versa, that arrival time of B is less than the arrival time of A, then we can say that B is the parent and A is our children. So, did you guys get the concept? Okay, if you guys got the concept, then I will show you this with the help of an intuition and an example. I have written down the same example over here. Just keep a note, okay, that the arrival time will be written in blue. Arrival time is written in blue, and the departure time is written in black. I have not yet written, okay, I am just telling you guys first so you guys don't get confused. Okay, let's start from our root. First we will visit this node. The time is 1. At time 1 we visit that node. Then root left right. Okay, we are going to left. We visit this node. Then we visit this node. And then this node. Okay, now it's over. Now it will traverse all its children. So at what time will it traverse all its children? The departure time for node 8 would be 5. Okay, the departure time for the node 8 will be 5. Now we go back here and we come here. What is the arrival time of node 9? It is 6. Node 9, the arrival time is 6. Then it goes to left. Arrival time of 12 is 7. Now we will traverse all the children of 7. And in what time will we do that? At the 8. Okay, we come back 8. We go here, we come here, the right one. It will be 9. Again we traverse all its children's. That time will be 10. Okay, after doing that, now see, all the children of node 9 are traversed. So it will come here and it will assign the departure time over here as 11. Again it will come back, all the children of 4 are traversed. Departure time is 12. Now the departure time of 2, it will not be assigned. Why? Yet we have to traverse this subtree. Okay, yet the right child is remaining. Okay, so we'll go here. It's 12 departure time. So at 15, at 5 we will arrive at 13, and at 10 we will arrive at 14. Now does 10 have any children? So at what time it will be departed at 15, and 5 it will departed at 16. And now 2, as all the children are traversed, it will be departed at 17. So what example I had chosen? 2 and 9. Okay, let's check it out. Let's check it out, guys. 2 and 9. This is the arrival time and departure time. What is arrival time of 2? It's 2. Arrival time of 9 is 6. This is greater, first condition. Departure time of 9 is 11. Departure time of 2 is 17. You guys can check here. Arrival time of B is greater, means this is node B, and departure time of B is less. Departure time of B is less. So in this case, what will happen? 2 is the ancestor of 9. Okay, you guys understood? This was the example which I had chosen. So let's continue. Now where were we? We were over here. It's 17. Okay, we jump over here. 18. We jump to 6. 19. So all the children of 6 means no children, but we have to say that will be traversed in 20. We come over here. 7, 21, 11, 22, 23. So at what time all the children of 14 will be traversed? At 24. Of 22, 25. Of 7, 26. Of 3, okay, and 27. And of 1 at 28. Okay, so this is how our arrival time and our departure time will be calculated. Okay, guys, keep this in mind. If you guys didn't understood this, you can just rewind the video. I have written it very clearly and the different colors. I have also mentioned what is arrival and departure time denoted in. Okay, so if you guys understood this, let's jump to the code. And in code, I will tell you which functions I have implemented and how the things are working out. Okay, so this is the code. This is my main function. Here I have constructed the binary tree of this diagram. Okay, same diagram I have constructed. And as I said, a hash map for arrival time and departure time. And this is our time 0. So we are doing a pre-order DFS. Why DFS? Because see, if I am at node 4, I am not storing both the nodes in a queue, the 8 and 9. I am only traversing one at a time. Okay, that's why a DFS in a simpler form I wrote that for understanding. So while traversing this function, pre-order DFS, what it is? If the root is null, see, if this root is null, if the children is null, I will not increase the time. There is no need to increase the time. And if I am reaching that node for the first time, then I will put that in the arrival hash map with plus time. Why plus? Because it starts from 0. Okay, so I am putting there as 1, and then this is a int. Okay, to return int. What will it return? The time to this function. Like suppose I am at node 4, it will return 12 at the end. At what time all its students are being traversed. Okay, it will return that. So first it goes to the left, as I said, then it goes to the right, and then after coming back from both the children's, it will then insert its time in the departure hash map. Okay, and this will return the time as I mentioned. Okay, so this is a simple function for pre-order, and this is a check function. So what this check function is written is, I'm not retaining the values. Keep in mind, I'm retaining the node locations. I'm not storing values. I'm retaining the node locations. So first is 3 and 14. Okay, let's come over here. Okay, 3 and 14. Yes, if I traverse to 14, 3 comes in the path. So this answer should be yes. Okay, 12 and 2. 12 and 2, yes, even this is possible. This is 2, this is 12. 4 and 5. No, I have taken this example. 4 and 5, they are not in the same path at all. And even here, what I have done is I have created a new node. Okay, new node, but as value 4. So what it will say is that this node is not present in my tree. But you guys might say, but the node 4 is present in our tree. But what I said, I'm not storing the node values, I'm storing the node locations. Okay, I'm showing the location of the node. So see, in this function, what my first condition is, that if either of the values are not present in my hash map, I will say this node is not present in the tree. I need to return false. Otherwise, this is my condition for the ancestor, and this is if it's the vice versa. Okay, this is the simple if else condition. Now let's run the code and check what the output is. As I said for the last example, node 4 or node 5 is not present in the actual tree, and node 3 is an ancestor of 14. Yes, node 3 is an ancestor. Node 12 is a direct descendant of 2. Node 12, descendant means a child kind of. Okay, node 12 is a children of 2. Yes. 4 is neither an ancestor nor a descendant. As I mentioned, these two nodes are nowhere near each other in the same path. So that's the answer, and I mentioned for this last node. So if you guys understood the intuition, like the video and share this with your friends, and please subscribe to my channel for more videos like this. Thank you.